Modern enterprise compute fabrics are composed of a physical hierarchy: Compute Express Link controllers, data processing units, and top-of-rack switches. These systems face a primary scaling limit because network orchestration still relies on reactive classical queuing theory. This reactive model causes microbursts and memory stalls during distributed AI lookups, particularly when running retrieval-augmented generation at scale. The impact is even more severe during massive mixture of experts training, where gradient communication bottlenecks limit the effective utilization of expensive hardware. Tensor Networks Inc. has proposed a different path to solve these compute bottlenecks, applying the mathematics of tensor network quantum gravity directly to silicon operations. This approach is operationalized through the Predictive Tensor Control Plane, a software layer running these calculations across standard data center hardware. Scaling next-generation hardware requires us to model infrastructure as a quantum entanglement network, rather than a series of reactive queues. This framework bridges theoretical quantum information physics with enterprise hardware control. The first translation maps entanglement entropy to normalized link capacity. Standard bandwidth allocation often fails to predict queue saturation during high-dimensional workloads because it lacks a predictive model for network density. Calculating the entanglement entropy of the network allows the system to normalize link capacity, preventing microbursts before they occur. The second mapping utilizes the concept of the minimal cut. Poor placement of the key-value cache in distributed LLM architectures creates extreme latency, slowing down token generation. The minimal cut calculation instantly identifies these critical bottlenecks across the fabric of the system. By identifying this cut, the control plane can proactively optimize memory tiering across the Compute Express link. Variables designed to measure quantum states now provide a deterministic formula for physical memory allocation. Within this framework, data routing becomes a problem of geometric navigation rather than a count of physical switch hops. Data centers produce an immense volume of telemetry, tracking queue depth, PCIe saturation, and jitter in real time. To make this high-dimensional data usable, the system compresses it into low-rank TensorTrain cores. The third mapping, graph curvature, uses this compressed telemetry to calculate a dimensionless information geometric link length. This enables geodesic routing, where data streams bypass congestion by following the mathematical curves of the topography. The final theoretical mapping is action extremization. This process incorporates a conditional value-at-risk penalty to guarantee that all automated hardware adjustments remain within safe, bounded limits. Packets follow the mathematical route of least physical resistance, ensuring deterministic performance across the fabric. This operational framework translates from enterprise data centers to contested defense environments. These domains face active electronic jamming and the constant threat that physical node destruction. The control plane is deployed across the tactical hierarchy, from sensing edges to command gateways. When electronic warfare degrades a link, the topology engine treats the mesh as an adaptive tensor graph state, automatically proposing new edges to heal the network. This resilience is a requirement for multi-agent autonomous systems, such as drone swarms, which require unhijackable verification of agent intent. Security is enforced through payload-blind topological caging. The system calculates a topological defect score for every agent, monitoring curvature gradients to identify anomalous behavior. Compromised nodes are isolated based on structural evidence, restricting the impact of living off the land tactics without needing to decrypt the payload data. The graph topology acts as a zero-trust perimeter, allowing defenders to contain threats based on connectivity patterns, even when those agents hide their intent within encrypted traffic. Returning to the commercial data center floor, the technical advantage of this framework is grounded in immediate hardware efficiency. Local edge agents evaluate conditional probability vectors within the tensor cores. By analyzing workload phase telemetry, these agents predict upcoming memory stalls with high precision. The system pre-warms pooled CXL memory independently, just before the CPU issues a formal page request. This predictive orchestration eliminates cache spills and significantly reduces token generation latency for AI inference. This technology is strategically viable because it is vendor-neutral. It deploys as a software overlay on existing SmartNICs and switches, requiring no expensive infrastructure replacement. The strategic edge in compute scaling has moved from physical hardware expansion to the mathematical orchestration of data flows.